3.6, the chain rule. This is the next in our list of rules for taking derivatives of sort of complicated functions. We know how to find derivatives of certain basic functions. We know how to find derivatives of variables raised to the power. We know how to find sums and differences of the derivatives of sums and differences of functions. We know how to find the derivatives of products and quotients of functions. What we don't know yet is how to take the derivative of a function that comes from what we call composition, where one function becomes the input to another function. So that's our topic here. And it's true the rules are written at the top of your paper. I'm not expecting you to know the rules yet. But I want to explore this first example and see if we can kind of understand where the chain rule comes from. I'm so sorry, they're doing construction next door. I moved to Mr. Kramer's room just for this. Now I'm in Miss Felix's room. So example here, if I have y is the function 2 times u, and u is the function 3x minus 5. So part A, can you write y as a function of x? I'm going to write it bigger down here. So I think you can do that. So y is 2 times u, but we know u is 3x minus 5. You could simplify that. Y is 6x minus 10. So we haven't done any calculus yet. We're just sort of remembering this technique you learned in Algebra 2 or pre-calculus about composing functions. So once I have an expression for y, can I find dy dx? Yes, I can. I expect you have no problem figuring out that dy dx is 6. So what is dy du? Well, here's the y function. Dy du means take the derivative of y with respect to u, which means take the derivative of y as if u was the only variable in the y function, which, if I look here in this box, u is the only variable. So the derivative of y with respect to u is 2. And what is the derivative of u with respect to x? Well, here's the u function. X is the only variable, so I can take the derivative with respect to x. The derivative of u with respect to x is 3. So you can walk through a bunch of lots and lots of other examples. Let's do one more. This one's not on your paper, but I think it can be helpful. Let's do this one. Okay, so what if I have this function y? Y is 9x squared plus 6x plus 1, which is the same as saying y is 3x plus 1 squared. So I could think of y as a composite function. It could be the function 3x plus 1, then getting squared. So I could, like you probably never had to before today, but you could think of u as being 3x plus 1, and then y would be u squared. So consider finding the derivatives separately. When I have y written as a function of x, which is here, can you find that derivative? Yeah, I hope so. So the 2 is going to come down to the front and multiply the 9. So the derivative of 9x squared plus 6x plus 1 is 18x plus 6. What if, instead of using that function, I tried to find the derivatives of those 2 pieces separately? Well, if y is u squared, I can take the derivative of y with respect to u, and I get 2u. If u is 3x plus 1, I can take the derivative of u with respect to x and get 3. And just notice, so the 2 examples we looked at, this happened, the derivative, I have to scroll down, hold on. There we go. The derivative of y with respect to x is the same as the derivative of y with respect to u times the derivative of u with respect to x. So that's one of the 2 things written at the top of your notes paper. This is, over here, we call this function notation with the parentheses to mean functions. And here, I don't know what we call that, but like the other form of the derivative. So this is what we just saw. Dy dx is equal to dy du times du dx. And if we take a look at this other version, it's a way of writing the same thing. These are both examples of the chain rule. The derivative of a composed function is the derivative of the outside function, in this case the derivative of f, with the inside the same, times the derivative of the inside function. So take a look at the next example down. So first I'm going to show you what I'm not asking you to do on this paper, just to kind of connect it back to what we did. If I know h is sine of x squared plus x, I could break that up into little pieces. I could make a composite function. If I were going to use the notation I used in the last two examples, I would say y is sine of u, and u is x squared plus x. So y is sine of x squared plus x. So let's talk about another notation we could use to say the same thing. So when we talk about composite function notation, we could say f of g of x. F is what we call the outside function, and g is the inside function. The g is the first thing that happens to the input, and f is the last thing. So if that's what we're going to do, the outside function, I would say f of x is sine of x. The inside function, the first thing that happens to x, is it gets squared and then added to itself. So I'm going to use the rule from above. The rule from above, I'll let you scroll up. If h of x equals f of g of x, then h prime of x is f prime of g of x times g prime of x. So I'm going to write that here. H prime of x is going to be f prime of, well, what's the derivative of sine? Cosine. Of g of x. Well, here's g of x. Times the derivative of g, so g prime of x. Well, here's g of x. G prime is of x equals 2x plus 1. It's not cool that I broke onto a second line. 2x plus 1. This is our first example of using the chain rule with a function written in composite function notation. So if h of x is sine of x squared plus x, then h prime is the derivative of the outside function with the inside the same times the derivative of the inside function. So cosine of x squared plus x times 2x plus 1. To find h prime of 0, that's not new this section. H prime of 0 is going to simply be the h prime of x rule with all the x's replaced with 0. So it's going to be cosine of 0 squared plus 0 is 0 times 2 times 0 plus 1. Well, cosine of 0 is 1 times 2 times 0 is 0 plus 1 is 1. And simply evaluating the h prime function at x equals 0. You might remember one day we watched a part of the Calculus in 20 Minutes video. So this is what he's talking about when the guy in the video, I'm sorry, I don't know his name, talks about taking the derivative of BLOP. So the derivative of sine of BLOP is cosine of BLOP times the derivative of the BLOP. So the inside, the BLOP is that inside function, the first thing that happened to x before the outside function happened to x. So the reason the chain rule gets its name is because sometimes we have insides of insides of insides, and you could compose as many functions as you want. It's like Shrek says about trolls. It's like an onion. You're going to peel away like layers. So we could talk about this example. If g of t is tangent of 5 minus sine of 2t, find g prime of t. So here's what I want us to think about. We're going to take the derivative from the outside in. I'm going to write g, use the pen and write g prime of t is. I'm going to ask myself, what's the derivative of tangent? Well, that's secant squared of. The inside is going to stay the same. That's the g function, the inside function. So that was tangent of 5 minus sine 2t. It's going to be secant squared of 5 minus sine 2t. Now I'm going to multiply by the derivative of whatever was the inside. Well, the derivative oh, I'm sorry, the inside, I mean, was 5 minus sine of 2t. So I'm going to multiply by that thing's derivative. Well, the derivative of 5 is 0. The derivative of sine of 2t is cosine of 2t, but it was negative. That already had a closed parentheses on it. Now, that 2t, that was the inside to this function, I'm going to have to multiply by the derivative of that inside. What was the derivative of 2t? Times 2. So that's a great answer. You might notice on the AP test, the multiple choice section, they might rearrange those terms. These are all factors that are getting multiplied. You'll probably find g prime of t, if this were multiple choice, that would get rewritten. So it looks like negative 2 cosine of 2t times secant squared of 5 minus sine 2t. But notice that on the free response section, you have no obligation to simplify that. Just notice, since we have 3 functions composed together, tangent, 5 minus sine of, and 2 times, there will be 3 factors in our derivative. So I'll do this first one for you. I would like you to try these problems. This first one is sine of 2x is f, so f prime of x. So for me, when I think about this, the outside function is sining, and the inside function is multiplying by 2. So when I take the derivative, I'm going to take the derivative of the outside, derivative of sine is cosine, and leave the inside the same, and multiply by the derivative of the inside. That's a great answer on the multiple choice test. That would probably be written as 2 cosine of 2x. Free response section, feel free to leave it like that. So notice that pretty quickly I go from 2 functions to 3 composed functions. So make sure you're using the sort of that longer version of the chain rule. The derivative of the outside with the inside, the derivative of the inside, it might have a new derivative on the inside. Might have an inside that needs its derivative taken. So we're going to multiply all those derivatives together. We'll see you tomorrow.